This segment is on power transformers, and power transformers are the heart of a substation. So it's really important that you understand how they're constructed, how to interpret the gauges, understand kind of some of the things you can do to maintain them, and especially to understand how they're rated. So these are all important things. So here's a picture of a massive power transformer. Cooling is a big part of making transformers work. Really, all electrical equipment is rated based on heat, right? If it gets too hot, insulation melts and you have a failure. So the trick to getting a lot of power out of one of these suckers or through one of these suckers is to try to keep it cool. At least that's one of the ways to do it. Here's a little more moderately sized power transformer. Notice the fans on the cooling fins. These work on a principle of natural convection, so the oil inside the transformer naturally circulates through the radiators, and then for a little extra cooling you can turn the fans on across the radiators. So oil level becomes important. If oil level gets too low, then you lose the flow through the radiators. Here's a nice picture of these bushings. That's probably one of the most common places for a substation transformer to have trouble is the bushings. They're kind of hanging out there. They have a lot of electrical stress on them, and they have a fair amount of physical stress too because they're kind of swinging in the wind and they've got some terminations on them. Here's a picture of the inside of a three-phase power transformer. This power transformer used to be installed at a substation called the Gap substation. It's just south of Gillette. So here's the three phases, and the way these are built, the secondary is wound first. You can't really see that, it's on the inside, and then the primary is wound on the outside, and then those three coils are connected delta Y typically for power transformers. That's a very common arrangement, not the only, but that's a common one. And this one had a fault and blew apart. Notice the steel, and you can't really see it too well, but the wood, they're built very beefy. The principle here, well, a few things that go on with these. One, notice the spacing on the coils. That allows oil to circulate and keep the coils cool. So that's what the spacing is. And then the steel and the beefiness of these things is to deal with fault currents. When you have a lot of current flowing through these coils, there's a lot of magnetic forces associated with that. And with a lot of magnetic forces, you have torque, right? So things like to kind of come apart sometimes. Here's a substation transformer that failed in Bismarck, North Dakota. Well, I don't know if the substation transformer failed, but something failed and burned up the power transformer. Okay, so just looking really quickly, remember power transformers, these are isolation transformers. There's no electrical connection between the secondary and the primary circuit. I'm not going to do a transformer theory class for you. You've already done that. But a couple things you need to know when you're banking transformers and when you're working with transformers, you have to remember that they are totally separate circuits. That's why we often ground the secondary, because it's a separately derived circuit. There's just a magnetic connection. Another thing is the idea of polarity. Typically these primary windings, this would be H1, and this would be X1 over here, the secondary. And what that polarity means is that if they have the same polarity, when the voltage is high on the primary, it'll be instantaneously high on the primary. It'll be instantaneously high on the secondary. They have the same polarity, if you will. If you have a high voltage on the H1, then there'll be a low voltage down here on the sine wave. So there's different ways we can build these things. A lot of this is just for you when you see the nameplates to be able to understand them. I've got a nameplate or two I'll bring into class and we'll talk about them. Typically power transformers are oil. We have oil for insulation. In addition to, there's other types of insulations in there too, but the oil provides insulation and cooling. There are dry type transformers, but those are typically indoor transformers. The oil transformers are usually outside because you have extra fire and explosion concerns with oil. But with oil, you get a smaller package, right? You can get more kVA in a smaller box if you cool it and insulate it with oil as opposed to air. All right, we'll look at different shell type, core type. This isn't that important for the technician, but you might be curious what the differences are. We're dealing mostly with power transformers, but instrument and distribution transformers are very similar. And we'll mention polarity, and then the cooling becomes very important, these different types of cooling. And we're going to look at that too. So here's the two different construction types. Sometimes you'll see this on a nameplate. It'll say shell type or core type. All this means is shell type, there's some extra steel in the transformer, this extra steel on the outside. Whereas core type, you don't have that extra steel. You use the tank to kind of complete the circuit. So shell type has some advantages, however it's more expensive. Alright, some things you're going to see on the nameplate, and we're going to go through what some of these things mean. The voltages, kVA, BIL, some of these things. So let's take a look at some of these. Here's a nameplate. Notice the nameplate shows this one a delta Y configuration. Notice the primary leads are labeled H1, H2, H3, and the secondary leads X1, X2, X3. That's the normal convention. And XO means it's grounded or it's a neutral point. There's a diagram that shows the actual connections, and notice the taps. And these taps are they're set up so that if you apply the given voltage at that tap, in this case you will get 208 out, line to line, or line voltage. So essentially what this is doing is tapping the voltage down, right? This is rated 480, 208. So if you apply a higher voltage to it, you'll still get 208. So essentially you have tapped the voltage down by going, the secondary voltage down by going to tap 1. If you were to apply 503 to this third tap, you would get more than 208 out. And this would be raising the voltage, right? If you applied 480 at tap 7, you'd get more than 208 out. And the taps have to do with how you connect this sucker. And you see how by changing the tap, you add turns. And you might remember how that all worked from your theory class with turns, ratios, and whatnot. Notice this is a 30 kVA transformer. That means you can put 30 kVA on it, and that's 30 kV on the primary and on the secondary. We kind of ignore the losses on these things. The impedance, 8% impedance. So we're going to use that number in some calculations we'll do in class, show you what that does, but impedance has to do with you can figure out the maximum fault current that will flow through a transformer if you have a short. Let's see here. This is assumed 40 degrees ambient. That's when you can put the 30 kV on it. And here's the BIL. BIL has to do with how much voltage it can stand for just a little bit. Basic impulse insulation level. We'll look at that closer when we do surge arresters. And I think that's enough for that, dude. Here's a substation transformer. This came out of Antelope Substation. I apologize, it's not the best drawing. Delta Y, notice again, H1, H2, H3 on the primary, the high side. And then here's the low side, X's. This HV means the high voltage, LV low voltage. And notice this X. This X means it's a dual voltage transformer. There's a switch in here that you can put the windings in parallel or in series, just like a motor. Remember how motors were done. So if we put them in series, what voltage do you think we would be? And if we are in parallel, which voltage would it be? I think you know the answer to that, I hope. Notice the class. The class is how it's cooled. O means oil, N means natural, A means air, F means forced. So oil natural, air natural, oil natural, air forced. So these are two different ways you can go. Essentially, the oil will circulate through the radiators naturally, and air would convect over the radiators naturally, or you can turn the fans on in this case and get some forced air. And these ratings then correspond to that. So we'll do more of this in class, but for instance, if you have oil natural, which it always is, it just flows, there's no pumps on this transformer, and air forced, you could potentially put 16,800 kilovolt amperes through this transformer, and you would expect the windings at that point to increase in temperature by 65 degrees, and we assume an ambient of 40. 40 plus 65 is 105, so if we would expect with 16,800 kVA on and the fans going and at 40 degrees ambient C, we'd expect the windings to be at 105 degrees C. 100 degrees is kind of considered when insulation is golden, and above that we could start to lose a little life. So anyway, or you could choose to operate this transformer a little more conservatively and put a little less load on it, and this would be your temperature rise, and you'd be under 100, right? 55 plus 40 would be 95. Notice here the impedance of this guy, 7%. Sometimes that'll be Z. The BIL you can't see very well, but this says full wave impulse test, which is the same thing as BIL. It says the low voltage was tested at 75 kV, which should be good. So that's just an impulse for a little bit. Notice this is a 7,000 volt transformer, 75,000 volt impulse test. And then these here are different tap arrangements, again, to move the voltage. These are what we call no load taps. In other words, we change it de-energized.